All right, here we go with Chapter 1, Section 3, Average Speed. Remember, with this video, you can pause, rewind, slow down my speaking, speed up my speaking, whatever works best for you. Here we go. Here's our vocabulary preview. We have a scalar, which means we only care about the magnitude. So a scalar quantity only deals with the size of something, how big something is. Meanwhile, a vector deals with the size and direction. Speed is distance traveled per unit time, and it is a scalar quantity. If we're going 30 miles per hour, we're only talking about the speed, how far we have gone per hour. So that is scalar, no direction involved. If we said 30 miles per hour north, now we're dealing with a vector quantity because we've added in that direction. And that is called velocity, as we'll see in a second. Constant speed means the speed is not changing over time. Average speed is the total distance divided by the total time. Instantaneous speed is the speed at any given moment, at that exact time. Velocity, as I said, is speed with a direction. The Doppler effect is the apparent change in frequency of an object to the observer that is moving relative to the object. Kind of long, confusing definition there. We'll break it down later on. Reaction distance is the distance that a vehicle travels and the time it takes the driver to react. So with the what do you think, remember, this is what do you think. Be wrong with us. We're here to address any of your preconceptions about the world around you, and hopefully we'll adjust them by the end. If not, if you already know everything, that's great too. In the investigate, we took the motion detector and we ran the cars, and the cars traveled along the x-axis. And as they traveled along the x-axis, the motion detector was using echolocation to draw a graph that showed the position and how it changed over time. And with that graph, it's going to look a little something like this, where there was a lot of little bumps, and then we didn't have Tim on the x-axis, we actually had time. So forget that little typo there. And then when we have this wiggling going on with our graphs, we don't care about that. We only care about the trend line, the straight line that would go through the overall trend, just like you see with the graph on the right. That is the whole idea with this investigate. Moving on. Strobe photos show how far a car travels in a set amount of time. So if each of these dots represents a car, if you've seen a strobe light happening usually around Halloween time, the light flashes and then it's dark, and then the light flashes and then it's dark. Well, that's what's happening. If we have our car, the light has flashed, and a second goes by, and then it flashes again, and then a second goes by and it flashes again. When we're waving in a strobe light, it looks like this, where it's like here, and then it's here, and then it's here, right? And we do that, and we can see that. Or a fan is moving slowly, or appears to look like it's moving slowly. So with this, if the distance between each of these dots is equal, which it roughly is, then we would say the car is moving at a constant speed. And with this, it looks like we have a car here, and then a second goes by and a car's here. And we've only traveled this small amount of distance. So with a smaller amount of distance, that means we're moving a lot slower. Well, then the next second goes by, and we go more distance. So we're speeding up for these first three dots. And then we go even farther, and we're speeding up, and now we're going this steady speed. And then our distances start getting smaller, and that means we're slowing down. This is our main equation here. B average equals triangle D over triangle T. Now this triangle is the Greek letter delta. Delta. And what delta means is change. So delta equals change. Whenever you see that triangle for the rest of this year, it just means change. And to us, change means final. Sorry, technical difficulty there. So it's final minus your initial or your starting. Initial. Whatever it is. Initial. Okay, so if we're looking at position or distance traveled, as we are here, it's going to be our final position minus our starting position, or the initial position, divided by delta t. Delta means change, and change means final, minus our starting. A lot of times our time will be, there we go again for a fun little ride, will be 0, so we don't have to worry about that delta every single time. Here's an example. If you drive a distance of 400 meters in 6 seconds, what is your average speed? Well, remember from the last slide, our average speed is our change in our distance over our change in time. And if we know our distance is 400 meters and our time is 6 seconds, we can put in the units here. We can abbreviate meters as lowercase m and seconds as lowercase s. So 400 divided by 6 gives us 66.67 meters per second. It keeps going on and on and on, but 2 decimal points is how much we're going to rely on for each answer. Okay. Average speed is not the whole story. Average speed does not mean instantaneous speed. Instantaneous speed happens at an exact time. Meanwhile, an average speed is the total distance over the total time. So your car, when you're looking at how fast you're going, that's not your average speed. That is your instantaneous speed. If your car's speedometer says 70 miles an hour, then you are moving at that moment 70 miles an hour. As soon as it changes, then your speed changes also. Now, your average speed, if you drive in the car on a road trip for 10 hours and you stop, get gas, go to the bathroom, get food, whatever it is you need to do in 10 hours, then you're not actually traveling for 10 hours, right? Because as you make these stops, you have a velocity equal to 0. So that's going to reduce your total average velocity. All right, time for another example. You are traveling 35 meters per second. That's important. Let's underline that. Your reaction time, remember that from the beginning, is 0.2 seconds. Calculate the distance you travel during your reaction time. All right, so again, we can use this v equals delta d over delta t. And this time we're looking for distance. So we're not looking for the velocity because it's already given to us. So we are going to rearrange this equation. You can do it one of two ways. You can plug in the numbers from here and then rearrange as if you're in math class. Or what I prefer to do, because there's less chance of error, is just multiply each side to solve for the variable that you're looking for. In this case is d. When we multiply each side by delta t, that makes the denominator go away. And what we're left with, I'm going to get rid of the deltas, is d equals v times t. Got rid of the deltas just to make it short and easier for us to look at. Now we can easily plug in our speed, which is 35 meters per second, times the time, which is 0.2 seconds, and we see how far we actually traveled. So 35 meters per second is pretty quick, and then we have 0.2 seconds. So 35 times 0.2, the total distance that we've traveled is 7. What about the units here? It's important that we have units. So let's see what happens. We're multiplying